Hello everyone, and today we are going to talk about limit, continuity and differentiation of functions of complex variable. In the last lecture we defined uh, the stereographic projections and we discussed about some functions of a complex variable, and in the other lecture we discussed some essential definitions. So today we are going to dive into the calculus of the complex variables, or so to say the complex calculus. So without further ado, let us first define what is a limit. So just like real variable calculus, let's say you have a function like this, f of z, which is a function of a complex variable, and let's say this z, the argument over here, it goes to z naught, another complex number or some complex number or some constant complex number, whatever you want to call it. And if this z approaches this z naught, and for that this f of z, let's say, approaches this w naught, then we say this whole thing in a mathematical term we state it like this, that is limit z goes to z naught, f of z is equals to w. This is the thing we write. That means z is going to z naught, and as a result f of z is going or approaching towards the value of w naught. But there are more conditions to it, and those conditions are that if we have this, that is mathematically we say limit of z goes to z naught, and if in such a way that f of z goes to w naught, if for every epsilon greater than 0, where epsilon is sufficiently small, or so to say very small, if for every epsilon greater than 0 there exists, this symbol means there exists a delta which is greater than 0, such that the modulus of f of z minus w, that means the difference between these two values, is less than epsilon whenever the difference between the values of z and z naught satisfies this equality. So what does this thing mean? Well, this epsilon and delta, both of them are greater than 0, but they are sufficiently small, especially the epsilon itself. Now, when the difference between f of z and w naught is less than this epsilon, then for every epsilon you can find a delta that will satisfy this inequality over here. Let's mark it with a star. So this very existence of limit, or you can say that this w naught will be the limit of f of z when z goes to z naught, if and only if this condition below is satisfied. And this is the rigorous definition of a limit. Now we won't bother with the rigorous definition that much, but it is important to keep this in the back of your head, especially if you are given a task where this whole expression is given and you are asked to show that this w naught is indeed the limit of f of z, and only then at first you need to find or define an epsilon like this, and then you have to find the deltas, and if you find such delta that satisfies this inequality, then whatever is given in the question or in the problem, that is correct, otherwise it's not. And you can ask that, can we calculate limits like just like we did in single variable calculus? Well, yes, there are subtleties, but we will avoid that for now. So let us take an example out of Ablowitz. This is an example from Ablowitz. And first we want to see what is the limit of this thing. 2z squared plus 2iz plus 4 divided by z minus I. And you can factor out these two just like real variable calculus. Then you can factor out this z squared plus 2z plus 4, I mean z squared iz plus 4 in the following manner, in terms of a middle term breakup, if you want to call it like that. This will be just z plus 2i, z minus I divided by z minus I, and if you calculate the limit, this is just 6i. Now, is 6i actually the limit of this function given over here? Let's check with the help of epsilon and deltas. So this is the epsilon delta check. And first we need some epsilon, right? And how do we get that? We take the function itself and we take the limit, that is this guy over here, 6i. So this is our function. The function is something like this, 2, and there will be z squared plus iz plus 2 divided by z minus I, and then you give a modulus thing. Oops, sorry, it should be minus 6i. This is less than epsilon, right? And now what you can do, you can again factor them out. That means you can use this line over here to simplify things, and what you will get after doing this is that you'll have 2z plus 4iz. Oops, sorry, there shouldn't be a z, it's just 4i, and then you have a minus 6i, right? So this is less than epsilon. And then after this line, let's go down below, you have modulus of 2z plus, sorry, it should be a minus 2i less than epsilon, or you can write it as z minus I is modulus of z minus I is less than epsilon by 2. So this is one way, or so to say one part. Now for this epsilon by 2, which you can also represent with, let's say, epsilon prime, which is less than epsilon, because obviously 1 by half is less than 1. So this is something like that. You can always replace them. Now you ask, okay, can I find some delta for this epsilon by 2, or so to say epsilon prime, that will satisfy this inequality over here, z minus z naught, where in our problem this z naught is just I. So we want to see whether we can find this kind of delta, right? So we want to see if we can find deltas, or deltas such that 0 less than z minus I modulus is equals to less than delta. Yeah, so this is the thing we want to see, and from here we can use this inequality over here, right? So if you use this two inequality, that is modulus of z minus I is less than delta and modulus of z minus I is less than epsilon by 2, you can immediately conclude that since z is not equals to I, because we are dealing with the limit problem, you can immediately conclude that delta should be something like epsilon by 2. So if you have some epsilon, you will always have some delta. So that's the thing. That means this 6i is indeed the limit for the problem we considered over here. Again, epsilon delta is not very important for us, but it's better to know how these things work. So this method will work for any z naught that is finite. in this lecture we are going to talk about infinite limits as well, but that will be very brief. To deal with limits that approaches infinity, we will need some theorems that will be discussed in the example video. So let me just state a theory here, that if your z goes to infinity, when you deal with the extended complex plane, you can have those points at infinity. So if this is the case, then the limit is written like this. And here, for every epsilon greater than 0, which is again sufficiently small, there should be a delta that is greater than 0, and this time the condition will be something like this. This condition stays the same. However, we have another condition. That means this fz minus w naught, modulus of it is less than epsilon whenever the modulus of z would be greater than 1 upon delta. So that's the kind of change that you expect when this limit z goes to infinity. One way to evaluate limits involving infinity is to just take the complex variable, take its reciprocal. That means instead of z you will use 1 by z, and instead of z goes to infinity you will use z goes to 0. But we will see that in the next video, and we will use 3 theorems that will actually give us more precise ways of calculating limits involving infinity. And as you can guess already, that limit itself is a linear operator, so all the properties that you see in your real variable calculus will also apply over here. That means properties like this: limit of z goes to z naught. If you have two functions, let's say f of z, h of z, this is just limit of z goes to z naught, f of z, limit of z goes to z naught, h of z. Obviously, since this is a linear operator, you can also use the scalar multiplicative thing. That means if you had a scalar like this, a and b over here, they would just be on the outside, nb. And properties like this that you see in your single variable calculus or real variable calculus also applies here. This would be just, let's say, w and s naught, where s naught is just this guy, limit of z goes to z naught of h of z. This is written as s naught, and this is written as w naught, so on and so forth. So this is the theoretical discussion of limits. Now let's discuss continuity. Just like single variable calculus, we are defining continuity in the following manner. If you have a limit when z goes to z naught, and the value of the function at point z naught, if they are equal to each other, then at that point this function f of z will be called continuous. Okay, and again, just like I said in the last lecture, that so far we are only dealing with functions that are single variable and uniquely defined. We will deal with the multi-valued functions later, because that will involve something called branch point, branch cuts, and Riemann surfaces. So please keep that in mind. And this is the definition of continuity. And after obviously there are some epsilon delta things that also comes when you have to check whether a function is continuous or not, but we are not going to dive into that. And we say that a function is continuous in a region if it is continuous at every point in that region. So this is something important to remember, because you are dealing with a complex plane, right? And you can have some region and there should be a function. You can define it over here in this region. Let's say you are defining a function f of z, and this function is said to be continuous if it's continuous at each and every point in this region. So this is one way to see it, and it's uniformly continuous in a region if it is independent of the point z is equals to z naught. So that is another way of saying that this function is just continuous inside this region. And by uniformity, it means that it doesn't depend on which point you are experimenting on. That means the point z0. Okay, you can easily show that the continuity of a complex function, that means function of a complex variable, if the function is said to be continuous, then the real and imaginary parts of the complex function, that means f of z, implies that it is continuous. That means if you write it like this, f of z is equals to u xy plus I vy xy, sorry, and if these two parts are separately continuous, you can also say that this is continuous. Again, we are not going to the proof, and that will be the theoretical discussion of continuity. And finally, the thing we want to discuss today is that the thing called derivative and differentiability, and let's call it differentiability. Just like real variable calculus, the derivative of a complex function is defined as follows. Let's say you have a function f of z and you want to find the derivative of that function at some point z0. So this f prime, that means the first derivative with respect to z at point z0, is defined as limit of del z goes to 0, f of z plus del z minus f of z by del z. If this limit exists, sorry, it shouldn't be yeah, okay, del z goes to 0, yeah, where del z is just z minus z0. So as I was saying, if this limit exists, only then you can say that the function is differentiable at that point z0. Okay, so it is just like all the thing that we see in real variable, but when we are talking about differentiability, we have to keep in mind that we are not working in a one-dimensional plane. Just like I mean by one-dimensional plane, I mean a one-dimensional line, like in real variable calculus, because in real variable you would just move along on the left or right hand side of the x-axis only if you have a function, let's say y is equals to f of x. But here in this complex case, you are dealing with a plane like this, where x and y, both of them can vary simultaneously. So that's why it is important that to make this definition very precise, that means the existence of differentiability actually depends on from where you approach. What I mean is that, let's say you are approaching along the positive x-axis and you find some values for this f prime of z0, and if you approach from the negative z-axis and you find some other value, then that function at that point will not be differentiable. So it is of crucial importance that the direction of approach to z0 should be independent. So let me just write this thing down formally. That is, the derivative only exists, the derivative that means f of z0, f prime of z0 should produce a unique value regardless of the direction of approach. That means let's say this is our plane. You are starting from here, let's say this is point A, and you are going towards this point z0, and let's say you get some value if okay, let's call that value w0. Okay, and let's say your friend starts from here, point B, and he is going like this and approaching this z0, and let's say he is getting another value w1, and you can have many different approaches and you can have many different values, but all these values should be equal to each other if the function is actually differentiable at that point z0. If you get different values, that means it's not differentiable at that point. So as a result, the derivative itself doesn't exist. Okay, now let's consider an example that will actually show us that this uh, preferred direction, or so to say, or is there any kind of preference when we compute derivatives in the complex variable, has an effect or not. So again, we're going to consider another example from Ablowitz, and you can find this example in Churchill's book as well. And this is a very classic example where your function itself is defined as f of z is equals to z bar. Okay, and so let's try to see if we can define, or we are trying to compute a derivative, and we want to see whether the derivative itself actually exists at some point. Okay, and again here this del z means z minus z naught, where z naught is arbitrary. That means it can be any point in the complex plane. So this limit del z goes to 0, and what we're going to do, we're going to have f of z plus del z minus f of z divided by del z. So limit del z goes to 0, this is just del z. So what is this f of z doing? It's taking some z and it is spitting out a z bar, right? So here it's taking input as z plus del z, so it should be z bar plus del z bar. If you are asking, okay, it should be something like z plus del z bar whole bar, then you can easily show that this bar just breaks down. This is a very easy exercise to do, so that's why I'm not showing it in details over here. So this is what you have ultimately. You have a del z and you have a del z bar over here. Okay, now there are two ways you can approach this problem. One of them is that you use the Cartesian representation. So let's try to see what happens when there is this Cartesian representation. So we are going to do it in the hard way, because in the book they use the polar representation. So why don't we try the Cartesian representation and see what happens. Okay, so this would be just x minus I del y, and that would be x plus I del y. So notice here, this del x plus I del y, that itself goes to 0, right? So that means instead of writing it like this, I should have written it like this: del x goes to 0 and del y goes to 0, right? And in the complex plane, this del x and del y, they can be related with each other through some parameters. You can even do that. That means let's say you have a curve like this in the complex plane, let's call it gamma, and gamma is some parameter of t, then this would be represented with x of t plus iy of t. But we'll discuss these things in the later lectures, where we will discuss more about integrations and all that. So for now, let's take the simplest case, and let's consider the case where you approach from the left, that means from the positive x-axis, and there is no y thing, right? That means you are moving in this direction. So this is our case 1. So again, this is case 1, and let's see, in this way there is no y component. That means these y's, they would be 0 by default. And what do you have in the end? You have just 1. That means if you evaluate this limit, this is just 1, right? Okay, good. So this is our case 1 result, 1. Now consider case 2, where you approach in this direction. That means you approach from left to right, that means along this green line. So again, in this case there is no y, right? So the result should be the same. Okay, that's great. So we don't need to calculate that. How about case 3, where you approach from top to bottom? That means you are approaching along the imaginary axis itself. Here del x is 0, but y is not, because This is the imaginary axis, and as you approach along this line, you are picking up values of y, right? So in this case, that means in our case 3, we can see that this limit del x goes to 0, del y goes to 0 will actually boil down, because these x's are now 0, and in the numerator you have minus I del y, and in the denominator you have I del y, right? And this is just what? Minus 1. So as you can see, these two results are not the same. And since we were doing it for any arbitrary points, remember, because here this del z was defined as z minus z naught, where z naught itself is arbitrary. So from case 1 and case 3, we can see that first of all, this function f of z, which is equals to z bar, is not differentiable. And as a bonus, since we're dealing with an arbitrary point, by denoting the arbitrary point z naught, what we actually did over here is that we proved that this function is not differentiable on anywhere in the complex plane. So this is a pretty interesting result, that even though the function seems pretty innocent, but you will see after you do some calculations that it's not actually differentiable anywhere. And before I finish off, I want to remind you that differentiability or continuity, they are related with each other as they were related in the single variable calculus. That is, if you have a continuous function, that doesn't mean it's differentiable. For example, this z bar function, it's continuous everywhere, but as you can see, it's not differentiable. However, if you have a function that is differentiable, that would be continuous. So these are the small details that you need to know. And before I finish off, again, I would like to list some properties that you have seen in your real variable calculus. Is that if you have two functions, let's say a of z and b of z, and you want to take the derivative of the whole thing, that means you want to differentiate, or so to say complex differentiate these functions of complex variable like this. Again, differentiation is a linear operator, so this would apply as well. That means all the things you see in your real variable calculus, you can just apply it on the complex variable as well. Even the quotient rule, let's say a by b prime, this would be just a prime b minus b prime a divided by b squared, so on and so forth. So this will be it for today. And before I finish off, I can give you a small exercise that you should be able to show that dd of z e to the power z is just e to the power z as well. There are many ways you can do it. You can take the series representation, you can use the definition of the derivative as well, and in fact you can also try to show that the derivative of sine z is just cosine z, and so on and so forth. So there are many ways to do it. You can even use the polar representations that is given by r e to the power I theta and so on. So why we are actually interested in this differentiation apart from all these things? Because from our next lecture we will go on and discuss something called analytic functions or holomorphic functions, and that will be very important for us. So that's why we want to know about the small details of this continuity and differentiability. So this will be it for today, and I'll see you guys on the next lecture. Thank you.